discuss about what is the allowed energies for free electrons in solid. That is the first question that you have answered last time. And then the second, the question is, what is the density of allowed energies in between E and E plus delta E. Things like that, right? That was the second question that we answered the last time. Now, today, we're going to answer the question, what is the free electron energies? In other words, what is the probability of free electrons to occupy the allowed energies? Okay, so in order to answer that, the final question, we have seen last time that the allowed energies per volume, allowed energy density is proportional to square root of energies, and E is proportional to square root of energy. Something like this, right? That's what we have seen last time. So in a metal case, the free electrons is filled up to Fermi energy levels, Fermi energies. The maximum energy that free electron can have in a metal system. We are going to talk about the other systems like semiconductors and insulators later, but for now we're talking about the free electrons, and the free electrons is most popular in the metal case. So we can say that for the Fermi energies. But if you talk about the semiconductors and the insulator, then the definition of Fermi energy is a little bit different from that, the maximum energy thing in the metal system. So we're going to talk about it in a minute. Okay. Now, in order to find out the occupancy, then we have to talk about the probability. And there are three statistics shown in your textbook. One is the Boltzmann statistic and the Bose-Einstein statistics and the Fermi-Dirac statistics. Three statistics are most popular. Okay, the Boltzmann statistics is well known that can be written as E star over KT, where the E star is the activation energies, activation energy for some system. Okay, and the Bose-Einstein is a little bit different. And this will be applied for the photons, the light particle, phonons, the lattice wave particle or picture of the lattice wave. It is applied to the Bose-Einstein, and then the probability itself is going to look like this: E over KT minus 1, okay? And then you can say this is a E star. Now, the Fermi-Dirac statistics, which has to be applied to the electrons and electron and hole, and the main characteristic electron, hole, and a proton. Okay. And the main characteristic of this Fermi-Dirac statistic is that the particles which obey the Pauli exclusion principle, Pauli exclusion principle, then the corresponding particle has to use a Fermi-Dirac statistics to find the occupancy of the available energies. And then it can be written as e to the E minus EF over KT plus 1, something like this. That is the Fermi-Dirac statistics. And here we can see the Fermi energies right there. And those three statistics, if you plot that in the probability and the energies, the Boltzmann goes something like this, okay? And then Bose-Einstein, it goes something like this. This is not actually 0, but it's close to this. This is going to approach, very large energies, but it goes like that. And the Fermi-Dirac, it stays something like this. This is a Fermi-Dirac, and this is a Bose-Einstein. This is a Boltzmann. The important thing here is that the high energies, all those three statistics approach it to the same probability. That is the important thing. The Fermi-Dirac statistics, in absolute 0 case, if it is Fermi energies, then the absolute zero, the temperature, the probability should show something like this, right? But at elevated temperature, then you're going to have spillover. This part is going to move to beyond the fermi energies at elevated temperature at T is greater than 0. This is T is absolute 0 temperature. That's what going to look like in the Fermi-Dirac statistics. Well, every statistics approach to Boltzmann at the high energies, sometimes in real practice, it is not the bad assumption to take everything into the Boltzmann statistics when Boltzmann statistics is that important. So let's just talk a little bit more about the Boltzmann statistics, okay? Boltzmann. Statistics. Mainly, that is, they can be written as something like this. And this N is the available state, okay? And this N is actually the successful number, which overcomes the activation energy E star. And E star is the activation energies for that process happen, for the process happen. To happen. Okay? And the two things can be noticed from this equation. This is, of course, this is the statistics itself, okay? One is when we take a log of this, E star over K and 1 over T. It should show something like this. So when you plot that log N, that is a successful number, okay? And then if you plot that 1 over T, something like this, then the important thing is we're going to have a straight line, and this straight line is corresponding to E star over K. So for some events that we have, if you can measure the successful affairs with respect to the temperature of the system, then from the slope we can understand the basic mechanism by knowing the E star from this straight line, okay? So this is related to the basic mechanism of the reaction, For example, when you plot the oxidation of silicon, for example, of silicon, okay? Then we know the silicon is going to meet with oxygen and we're going to have a silicon oxide as a layer on top of this. And the typical temperature is about 1,000 degrees centigrade, something like that. And then if you measure the thickness so that this oxidation rate and then you can plot that with a temperature, reciprocal of the temperature, then you're going to have a straight line. And then this, you can deduce the E star, okay? You can deduce the E star. And then that E star is about 0.11 electron volts, something, sorry. This is about 1.9 electron volts, 1.9 electron volts. And this 1.9 electron volts is related to the bonding energy of a silicon. Bonding energy is related to the bonding energy of a silicon. Okay? Energy of silicon. So from this experiment, what we can see is that this oxidation reaction is nothing but a breaking of silicon bonding to have the oxygens to make the volume twice after the oxidation, things like that, okay? So this Boltzmann statistics is very important. It can give us the clue what is the basic mechanism for the reaction, okay? And number two, we can notice from this is that the Boltzmann constant. What is the Boltzmann constant? Boltzmann constant. This is the amazing thing, okay? Boltzmann constant. Boltzmann is actually a name of physicist, right? And it's so famous that we can put this Boltzmann constant K name after him, okay? And then this is amazing in a sense that when you have a temperature, okay, you can find out the energy corresponding to this by simply you multiply that with this Boltzmann constant. For example, room temperature. What is the room temperature? 300 K, right? That is in absolute temperature, we can say that is the room temperature. Okay? And you want to know what is the energy corresponding to this room temperature. Then all you have to do is just multiply that 300 with by the Boltzmann constant, and you end up with the number 0.025 electron volts. So the room temperature is just equal to the 0.025 electron volts. Okay? So in a semiconductor, sometimes when you elevate the temperature, the electrons in a semiconductor has a high mobilities, okay? And then there is a relationship between the temperature and the electron mobilities in the semiconductors. But even at room temperature, if you apply the high electric field, then electron can move very fast, okay? Then we want to know what is that electron velocity corresponding to the temperature, which happens by the electric field, okay? And then all you have to do is you find the velocity of the electrons, and then you know the mass, and then you get a kinetic energies by knowing the velocity of electrons, okay? And then this velocity happens by applying the electric field, not the temperature, okay? And then electric field, if you multiply the mobility, which is a material constant of silicon, which is 1420 centimeters square per volt sec. That is the mobility of electrons in the silicon. So if you apply some electric field, then you can get the velocity. And then you know the mass of the electrons, so that you know the kinetic energy of the electrons in the silicon by apply the electric field, not the temperature. Then you can get the kinetic energy number, and then if you divide it by the Boltzmann constant, then you end up with the temperature, right? And this temperature is corresponding to the kinetic energy of the electrons, which obtained by the electric field, not the temperature. So if you apply the high electric field at room temperature, the electron moves very fast, and then we can deduce the corresponding temperature. And then that temperature, that electron is a hot electron. We call that hot electron. This name hot is not coming from the temperature, but from the electric field. And it happens in the semiconductor devices. You know, the semiconductor devices is so micron-sized, so if you apply just the 3 to 5 volts, then you're going to create a huge electric field, easily 10,000, something like that, electric field as a volt to centimeter, okay? And then that electric field will give a high kinetic energy to the electrons, and it can be regarded as a hot electron. And hot electron effect in the semiconductor device is very, very important. Anyway, so I emphasize two things. One is the Boltzmann statistics is important, and the number one is we can understand the basic mechanism of the reaction by the Boltzmann statistics. And then the second thing is the Boltzmann constant is it's kind of factors we can convert from energy to temperature and temperature to energies, vice versa. Okay, so the questions we want to answer now is, what is the free electron energies? So in order to get that, if you say the Ne is number of free electrons, unity volume, with energy E, okay? This is going to be the available state, energy states corresponding to that energy, specific energy, times the probability of electrons to occupy that energy state, okay? So this is the main thing that we want to do. In order to find out the free electrons energies in the metal system, what we have to do is it should be applied. It should be applied to the semiconductors and insulators as well. But anyway, it's in order to find that energies in the metal system, you have to find out the available states, density, and the probability of electrons can occupy the energy states. So this is, we know this. We have been calculate that, and then that is 2 pi square 2m over h bar square 3/2. And the statistics here, this is the n sub e, right? N sub e. And we know that is proportional to the square root of E, energy itself. And then we want to multiply that with the Fermi-Dirac statistics, which is going to be something like this, which is going to look like that. And then if you actually multiply that, now the NE is going to look like this, right? Which is NE is proportional to the square root of E. And then the Fermi-Dirac statistics is going to run, it's not the same scale, but anyway, it is going to look like this. That is a Fermi-Dirac statistics. Fermi-Dirac statistics. And if you multiply this 2, you end up with something follows that. That is the N sub E going to be. And then here is the Fermi energies somewhere. It is not the maximum point, but the Fermi-Dirac statistic says the Fermi energy is 2 to 3 kT away from the maximum point. Okay? In the metal system. In metal system. So this is actually the energies of free electrons in a metal system. You integrate all the energies that the free electrons have and then multiply by that with the number of electrons. Then you integrate them, and then that is the energy of the metal system the electrons can have. Now we have, in the textbook, we have applications. So far we have built the free electron models. We have answered the 3 questions: what kind of energies available for the free electrons. You should remember this. What we are talking about here is that the free electrons in a metal system and the probability, the population of the free electron is around 5 times 10 to the 22 atoms per centimeter cube. That is a typical number of atom density in a single crystal of any typical metals, for example. And then if it is lithium or alkali metals, then each atom give up 1 free electron, so that the number of free electron is exactly the same to the number of atoms. Just like that. That is a free, right? And then what we have calculated is that what is the energy of each free electrons can have in this metal system. And it turned out just like this. Now, what we are going to do with this free electron models, okay? What is the application of this? If there is no applications, then we have discussed about this, we have built this free electron model for nothing, right? So, in the text, it has a photo emission, thermionic emission, and field emission, and heat capacity. And finally, spin paramagnetism of a metal system. All right? So I'm going to briefly introduce you about these applications, and then I'll give you a homework on the Monday, which you can understand of this applications more in detail. All right? So let me just give you the brief idea and how we can apply this free electron model to understand these phenomena. The first task was photo emission. Photo emission is you shine the light, and then the electrons is coming out from the metal surface. So you put a detector on the metal surface, and then you shine the light on the metal, then electrons are coming out. Okay? And then we know the work function of a metal. Basically, we are going to talk about the metal system, not the semiconductors and insulators, because in the semiconductors and insulators, we do not have many free electrons. So mainly the phenomena that we are going to discuss is about the metal system. The work function is the energy necessary to escape one free electrons from the metal surface into the vacuum, okay? And then if you shine the light and then you detect the number of free electrons coming out from the metal surface, okay, then you're going to have the current, the electron flow, the collection of electrons will give you the current, so that all you have to do is measure the current in the photo sensor, and then h bar omega photons, okay? This is the light intensity. Then you're going to have a straight line here, and then this intercept here is going to be the work functions corresponding to h omega minimum. And then that is the work function. And we call this Richardson what is it called? We have some name for this. Anyway, that is the work function. That is the photo emission. Now, the thermionic emission is the emitting of electron by the temperature. Thermionic emission. Emission of electrons by the temperature, okay? And then it is obvious that if you increase the temperature of the metal surface, then the electron is coming out. And then you have to remember that in a metal system, the this is the Fermi energies. And this is the electrons with that specific energies. For example, some of the electrons of the population here, this is a population of electrons, electron density, and these electrons will have this much energies. And this number of electrons will have this much energy, something like that, okay? So if you shine the light, what it means that is this energies of free electrons is going to increase its energies by the thermal energies, so that this shape is going to be changed. It is going to move some higher values, something like this, right? And then these high energies can overcome the work functions, the energy necessary for the electrons to escape from the metal. Okay? Then we are going to have some electrons emitted from the hot metal surface. So if you have electrons by the thermal energy, that is the thermal emission. If you have electrons coming out from the metal by the light, then we call them photo emissions. It's very simple. And then if you do the simple calculation, then you're going to have a Richardson equation. And then that Richardson equation, it says the current density that we can have is AT squared exponential minus Q phi over KT. Something like that. So if you plot the log J over T squared, and then take a log, then this slope is corresponding to Q phi over K. This is 1 over T. Okay? So these two methods, we can get the work function of the metal. And the next thing is the field emission. Field emission. Field emission means if you apply the high electric field to the metal surface, then the electrons will be excited and they're coming out from the metal surface. That's simple. Now, if you have a metal system, and then this is the Fermi energies, and after Fermi energies, all electrons are occupied, and then in this fashion, right? This is the free electron model that we have. So absolute to zero temperature, for example, all electrons have this maximum energy, and then it's just filled up with free electrons. Okay? And then in a vacuum, this is a vacuum, and this is x equal to 0. Then in a vacuum, the energy cannot be defined, but somewhere very high, so that the electrons cannot coming out to the vacuum at the normal situation. Then what's happening if you apply high electric field? Then this band is going to be banded like that, so that the energetic electrons close to nearby the Fermi energies, you can do the tunneling here. Tunneling to the vacuum, and that is the field emission. The electrons which can be obtained from this high electric field can give us the images of the atoms in the transmission electron microscopy. You know, the TEM, you make a sample very thin. How thin is this? This is going to be about 10 angstrom. or at most 100 angstrom. This thing. And then you make electrons by applying high electric field to the metal tip, very sharp metal tip, then electron is going to be made by the field emission. And those electrons is going to be accelerated with the electric field, okay, and then pass through it. And then if this layer has a regular atomic array, then electron is going to diffract in a regular fashion, okay, by Bragg reflection, Bragg law, so that it can give us the atomic images, something like this. What you are seeing here is not the atom itself. We are just looking at the shadow of atoms. So from this shadow, we just imagine the atom is going to look like a ball. We never seen, nobody can see the atom itself, okay? We just see, we are going to see the images or the shadow of the atoms. Anyway, so the field emission, we are going to have a tunneling probability, and then we can plot the current coming out from this electric field again, and then electric field, reciprocal of the electric field, you take a log of this, and then slope is corresponding to, proportional to the square root of phi, work function. Oh no, not square root, 1/3, 3/2. 3/2. Okay, we can get that equation, and that is coming from the tunneling probability. And the next thing that we can talk with this free electron model is that heat capacity. What is heat capacity? If you apply the metals and the temperature is going to increase, of course. If you heat the metal, then the temperature is going to increase. And that is due to the vibration of the atoms and electrons. So the temperature is going to increase as you apply the heat energies due to two things. One is vibration energy of lattice atoms. And number two is vibration energy of electrons, free electrons. Okay? So you distinguish those two contributions, and then the capacity the lattice contribution is proportional to the T third, okay, and then free electron contribution is proportional to T. So in a metal system, you have lattice atoms and the electron at the same time, so that if you plot the total capacitance is going to add those two things, right? So if you divide by that with the temperature, and then you plot that thing with the temperature, then what you're going to have is you're going to have a C over T is going to be something A t square plus B, okay, from here. Then if you plot that thing with the t square, then you're going to have a straight line, something like that. And then this is the value of, what is that? T is equal to, right? Yeah. This is the value of B, and then the slope is going to be A. So you can make a distinction between the lattice contribution and the electron contribution for the heat capacity of the metal system. Now, if you have an insulator or the semiconductors where this electron contribution is minimal, is negligible, then you're going to have a different plot in here. So you can distinguish. This is one way to distinguish whether the specimen is the metal or the semiconductor or the insulator. This is one way to make a distinction. Okay. Finally, the paramagnetism of the free electrons. Number 5, spin paramagnetism. Okay, again, we are talking about the metal system. You know, the magnetization is K, the magnetic susceptibility, and magnetic field. You have to, you know, this equation, and then the M is magnetic moment. H is a magnetic field. So if you have materials, if you have metals, if you apply the magnetic field, then the metal itself is going to be magnetized, okay? And you know, the paramagnetism is the magnetism only with the apply the electric field, a magnetic field, and the different thing is ferromagnetic, which the material can sustain its magnetic moment even after the application of the magnetic field. Okay, we are talking about the paramagnetism, and then this paramagnetism is the magnetism that exists only when the external electric field is applied, right? So if you make a free, band model for this, if you plot that E versus NE in this fashion, which is, you know, the energy we plotted NE versus E, and we are very familiar with this curve, right? Square root of E. You just tilt it 90 degrees, and then we're going to have this kind of curve, E versus NE, okay? You just change the X and Y axis in there. And if this is the Fermi energies, then free electrons is going to be Fermi energies, the free electron is going to be filled up to here, just like that. Okay? And then this part is spin up. You know, every electron has 4 quantum numbers, right? And that 4 quantum numbers should not be same in any sense, according to the Pauli exclusion principle. So when you draw something like this, then this negative side means the spin up, and this positive side is the spin down. Other things, the 3 quantum numbers are exactly the same. But the spin up and spin down can be distinguished just like that. And then the number up and down is exactly the same, so that without any magnetic field, this metal does not show any magnetism, because the spin up and spin down is exactly the same. Now, what's going to happen if you apply the electric field to this? Then, according to the direction of the magnetic field, if it is parallel, then this side electron is going to be increased with the sacrifice of this electrons. In other words, this electron is going to be flipped over. It's spilled over. It's moved to this favorable magnetic field directions. Right? So, if you change that, then we can have net magnetism, because all you have to do is just extract this part from this part, and we are going to have a net magnetism. That's how we are going to calculate here. And then with the magnetic field, then the energy can be written, magnetic energy can be written just like that, and then this mu B is a Bohr magnetron. Bohr magneton. Bohr magneton, that's a minimum substance, minimum unit of the magnetic moment, and then that is 0.27 times 10 to the minus 20 erg, something like that. It can be written like that, okay, in a Gaussian unit means. Anyway, so if you change that, then what you can think is, actually, if you draw, the Fermi energy is not going to be changed after the equilibrium with the application of the magnetic field. So this is what happening, but in your drawing, you have to keep the Fermi energy constant, so that the drawing is now going to be drawn something like this, so that electron is occupy all this part, something like that. And then this height now is going to be UBH. Okay? So the net magnetic moment now you can have is just number of, this is a number of electrons moved in favor of magnetic field, okay, times the magnetic moment that electron has, okay, mu B, okay, and that is going to be equal to the susceptibility and the magnetic field. So this part, you can have the K value, the susceptibility of the metal system, by using these free electron models. All you have to do is just to calculate the number, the areas corresponding to this. How you can get the number? You just multiply x and y. So the number of free electron moved in favor of H is nothing but the x times y times 2. Just rectangular in this part and then in this part. That has been moved to here. Okay, just x times y. Okay, and y is obviously mu bh. And then x is we know from here, we know this distance. That is going to be x here. Okay? So you just apply that free electron model to this. Then you have this number, and then you end up with this part is going to be 2 mu b h n at the Fermi energy level. This is the number of electron density of, and then the unit here. So that is corresponding to the magnetic susceptibility, and then the susceptibility is going to be 2 mu b square and EF. Now, here's the important thing in this analysis. The important in this analysis is that the paramagnetism in a metal system the magnetic susceptibility is going to be 2 mu b square and EF. Okay? And EF, the available energy density at the Fermi energies is m2h bar square pi square and then 3 pi square n 1/3 from the free electron models. Okay? And if you put that thing, you can see that the susceptibility is a function of n and proportional to n 1/3. N is the number of free electrons. Okay? Now, the important thing is paramagnetism in the metal susceptibility is not a function of temperature. That is the amazing thing. You know, the magnetism itself is very much dependent on the temperatures. Okay? So most of the devices, if it works with the magnetic field principle, then the temperature is kind of thing that you have to avoid. With the temperature, the magnetism is going to be completely